Imagine you're standing still, watching a train roll by. It makes perfect sense to us that things moving inside that train share its speed. If a passenger on board throws a baseball straight toward the front, you wouldn't just see the speed of the throw, you would see the speed of the ball added to the speed of the moving train. We can picture this as basic math. If the train is moving 50 miles per hour and the throw is 10 miles per hour, you add those two arrows together to get a total speed of 60 miles per hour. This is how motion works. But let's run that exact same scenario again. Only this time the passenger replaces the baseball with a flashlight, shining a beam of light off the front of the train. This is where our everyday math completely breaks down. You would expect the total speed of that beam to be the speed of the light plus the speed of the train. But it isn't. The train's forward momentum adds absolutely nothing to the light. Albert Einstein realized this wasn't a math error. It meant that light in a vacuum operates under its own set of rules. It is an independent, unbreakable constant. In physics, this constant is represented by the lowercase letter c, and it has an exact value, 299,792,458 meters per second. While a car or a baseball will always change speed depending on who is watching them move, light refuses to conform. No matter how fast you are traveling, light always outpaces you at that exact same rate, acting as the ultimate speed limit of the universe. Look at this blue pencil sitting inside a beaker of water. It looks like it has been snapped in half at the waterline, but this isn't just a random trick of the light. That famous speed limit has a specific condition. It strictly applies to a vacuum, a place where there is absolutely nothing for light to run into. But here on Earth, light is constantly moving through air, glass, and water. When light waves enter these materials, they collide with physical matter. Those interactions force the light to slow down. Scientists use a number called the refractive index to keep track of this. Think of it like a slow-down score. A higher number means the material is harder for light to push through, like trying to run through deep water instead of thin air. When light enters a denser material at an angle and slows down, its path actually bends. This bending effect, known as refraction, changes how our brains perceive the physical depth of the objects around us. We can see this in action with a coin at the bottom of a container of water. Because the light bouncing off the coin bends as it exits the water, the coin appears to be sitting much closer to the surface than it actually is. Those bent pencils and shallow coins are the visible results of light interacting with the physical world, showing us exactly what happens when a universal constant meets the friction of reality. In a universe where almost everything else is relative, having one measurement that never changes gives us a powerful baseline for understanding our world. For a long time, humanity measured distance using physical objects. The standard meter was once defined by the length of a physical metal bar, kept safely in a vault. But physical objects are unstable. Metal shrinks in the cold and expands in the heat. Over decades, those tiny shifts make it an unreliable foundation for science. In 1983, scientists decided to stop relying on objects that change and tied the definition of a meter to the one thing that never does: the speed of light. Today, a meter is defined as the distance light travels through a vacuum in a tiny, exact fraction of a second. Specifically, 1 over 299,792,458. Understanding how light behaves when it hits different materials has also allowed us to build the modern world. By engineering glass that bends light back inward, we can trap light pulses inside thin cables. This allows us to send information instantly across the planet, forming the physical backbone of the internet. The speed of light is the ultimate ruler. By using this fixed baseline, we can finally define the literal size and scale of the universe with absolute certainty.